let's discuss a couple of interesting applications where we can use Bernoulli's principle. Probably one of the biggest and best examples of Bernoulli's principle is an airplane wing. So here's what happens. You have um, streamlined air that moves over some mass that has a weird shape, an airplane wing shape. But before the air hits the wing, let's take a look here at two lines. So the area between two sets of lines, they may not be perfectly equal, but they're pretty close. But what happens to the area here? The area is relatively the same. So from that, we know that A1V1 has to equal A2V2. So at the bottom, V1 is relatively equal to V2. So not a whole lot's happening on the bottom. But let's go look at what's happening up on top. Because we saw two lines here have a certain distance apart, but they are much closer together. So the equation of continuity says A1V1 has to equal A2V2. Well, this area here has dropped significantly. And so the velocity has to increase. So the wind going over the top of an airplane wing has to be higher. All right, that's half of the story. The other half has to do with Bernoulli's equation. Density. I'm going to ignore the potential energy term just for a second. And we're going to focus on just the change in pressure and velocity. So on the bottom, we saw not much happened with the velocity. Maybe a slight change in velocity, not a whole lot. But on the top, the velocity increased really, really quickly. So we've got a nice, fast velocity. Okay, so the right side of the equation just increased. Well, how do we compensate for that increase? The pressure has to decrease. And so up here, you get a great big fat low pressure. And on the bottom, relatively speaking, you have a higher pressure. Well, whenever you have a difference in pressure, that's going to push air from high to low, and you get airplane lift. So that is how an airplane gets its lift when it flies. Here's another really cool experiment. We have a ball, just a simple baseball, that you throw towards home plate. So it's going this direction. So, but relatively speaking, the air's not moving, the ball's cutting through the air. But if you look from the point of view of the ball's holding still, the air is flowing past, and that's what you see here. So it's just relative motion. Okay. So again, we can watch the streamlines. Assuming that the ball just moves in a straight line, not much changes. The air keeps it moving in a straight line. But if you can add a curve to the ball, then here you've got the ball on the right side, the ball's moving upwards in the picture, which is counter the flow, counter the direction of the flow of air. Okay. As a result, basically, the apparent velocity here is much higher. Now on the left, your ball is moving downward in the same direction as the air. Comparatively speaking, that ball isn't moving quite as quickly next to the air, so you have a smaller velocity. Well, from Bernoulli's equation, if we have a high volume, excuse me, if we have a high velocity, that means we have a low pressure. And on the left side, if we have a low velocity, that means that we have a high pressure. Whenever you have a difference high to low, it pushes the ball, or air moves from high to low, and therefore your ball is actually going to curve. So that's how a curve ball works. By spinning the ball, it changes the velocity and the pressure on either side of the ball, causes the ball to spin. Now here's another really good application of the Bernoulli principle, and that has to do with the body itself. Now, two things I want to bring up in this picture. First of all, notice you have a constriction here. Okay. Normally, you would have blood flowing through this vessel, and then some of that blood would move up here, some of it would move on the other direction. So some would go up to the brain, the rest would go to the rest of the body. But if you have a constriction, then all of a sudden you've narrowed the area that blood can flow. And when you decrease the area, you have to increase the velocity. And if you increase the velocity, you decrease the pressure. So since the blood is now moving at a higher velocity, it's more likely to continue this direction. You're going to end up with very little flow, not much, just a little amount of flow to the brain. And so because of a constriction in the blood vessel, you end up getting a lack of blood going to the brain. And you end up having some pretty serious brain issues and more difficulties in concentration, in comprehension. It's tough when you have constrictions in your blood vessels. Now, this constriction could come from any number of things. It could come from a clot, which we definitely hope isn't what it is, because that would potentially not be very good for your health in the near future. Or it could come from tight muscles. If you have tight muscles, they're really constricted and they don't let the blood flow very easily. So somehow you need to stretch them out. Now, this being said, I want to turn my attention to something else in the body. When you wake up in the morning, you stretch. Well, good. What good does stretching do? Let's say that this, how about we do red, because a blood vessel is red. This is your blood vessel. Has some sort of area A there. Okay, and we get a velocity of blood through the vessel. But then you wake up in the morning and you stretch, meaning you push your arms out as far as you can and stretch everything, including the blood vessels. But what happens to your blood vessels when you stretch them? They get narrower. Well, continuity equation that says that when the area of the blood vessel decreases, the velocity increases. So, bam, you end up having faster blood flow. That is one reason why we stretch in the morning. There are a number of reasons, but one is to get the blood flowing a little bit faster. And once the blood starts flowing, you're more able to think clearly, and you get more oxygen to the blood a little bit faster, so on. Last but not least, perhaps people in industry or some mechanical work have used a Venturi meter. A Venturi meter is a device where you can actually measure the pressure in a fluid based on its velocity. There are other instruments that use this type of principle. say, a good classic example, you have something called an atomizer. You have a bottle with a fluid, and a straw comes down here into the fluid. That looks kind of weird. Let me do it this way. So we have a tube coming all the way down. We'll give it a fluid color. There we go. That looks better. Maybe. Anyway, so on top, you end up having a very narrow valve. That looks like this. And then on one side, you have a big bulb. A device like this may be used for something like perfume. What does it do? Well, when you squeeze on this bulb, so this is an easier way to say it. When you squeeze on that bulb, it causes the air to move with some velocity v. Bernoulli's principle: if the velocity increases, the pressure decreases. So you have a low pressure here, high pressure down here. What happens to your fluid? It flows right up your tube. And once it hits this high velocity air, where does it go? It gets sprayed out. And you've got yourself an atomizer or a perfume bottle or whatever you may want to use this for. Anyway, that's a very common use for the Venturi effect. And you can use Venturi meters to measure the pressure of a fluid as it flows through a pipe.